Let's take a look at this review problem. We're going to exactly evaluate the 6 series that we see on screen. And we will evaluate these using some of the series that we developed in class. All right, number one, we know that e to the x is equal to summation of n equals 0 to infinity x to the n over n factorial. That's a given series. Now, that's pretty much what I have here, except my x has been replaced by -1. So replacing x by -1, I know summation n equals 0 to infinity of -1 to the n over n factorial will be equal to e to the -1, or 1 over e. And so this expression here is simply equal to 1 over e. And this can be checked on a calculator. If you use your calculator to compute this, 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial, and so on. That should converge to 1 over e if you take enough terms. Okay, second question. This one I have an x to the 2n over 2n factorial. That reminds me of cosine. Cosine of x is given to be summation n equals 0 to infinity, -1 to the n, x to the 2n over 2n factorial. All right, and that's pretty much what I have here, except instead of an x, I've got a pi. And so therefore, summation n equals 0 to infinity of -1 to the n times pi, 2 to the n over 2n factorial. That will be equal to cosine of pi, and cosine of pi is equal to -1. So it's kind of remarkable that this very complicated sum works out to be -1 exactly, and there's no pi's left in it. Okay, number 3 requires a little bit more thought. -1 to the n over 2n plus 1 times 3 to the n. Okay, now I do have a series that has a 2n plus 1 in it and a -1 to the n in it, and that's the arctangent power series. Arctangent of x is equal to summation n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1. Okay, so that kind of matches what I have here. -1 to the n certainly matches, 2n plus 1 matches. So I need to get this to match. Instead of, I've got a 3 to the n. So let's, with this as my reference, let's now take a look at the original series here. So therefore, summation n equals 0 to infinity of -1 to the n over 2n plus 1 times 1/3 to the n. Okay, well, I can get this to be, I can get a 2n here by taking square roots. So this is equal to summation n equals 0 to infinity of -1 to the n over 2n plus 1. If I write this as 1 over 3 to the 1/2 to the 2n, then 2n times 1/2 is going to be equal to n. And so the exponents match by the laws of exponents. So I've got the square root of 3 here times 2n. So that's equal to summation n equals 0 to infinity of -1 to the n over 2n plus 1 times 1 over the square root of 3 to the 2n. Okay, now I can almost use the formula here, except I need a plus 1. So to get that plus 1, let's force that in. -1 to the n over 2n plus 1. Let's write this 1 over square root of 3 to the 2n plus 1. So I'm dividing by an extra square root of 3 in here. In order to compensate, I need to multiply by square root of 3 on the outside. Okay, now this exactly now matches the arctangent formula. So I have square root of 3 times the arctangent of 1 over the square root of 3. And the arctangent of square root of 3 is pi over 6. And so this sum works out to be pi times the square root of 3 all over 6. So this one took a little bit more work in order to make it fit the formula for a Taylor series. All right, let's continue. Number 4. Summation n equals 0 to infinity, negative 1 to the n, over 2n plus 1 factorial, pi over 6 to the 2n plus 1. Now, this fits the formula for sine of x. So I've got a 2n plus 1 factorial. I've got something to the 2n plus 1. And I know that sine of x is equal to summation n equals 0 to infinity of negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And so all I'm doing is replacing x by pi over 6. So this is going to be equal to sine of pi over 6. And so this very complicated expression turns out to be equal to only 1/2 all by itself. Okay, number 5. Summation n equals 0 to infinity 1 over n times 10 to the n. The base formula here, I notice I've got a n here on the bottom, and I already have, and I've got a power of n here. And so that suggests that I probably want to use the Taylor series for natural log of 1 plus x. And this is equal to summation n equals 1 to infinity of negative 1 to the n minus 1 times x to the n over n. And this works as long as x is between negative 1 and plus 1. And it actually does converge if x is equal to plus 1. Okay, now we want to make this fit the pattern that I see here. I've kind of got what I want here, except for the fact that I need to get rid of this minus. All right, so let's, what do I need to plug in to x in order to get the series that I see here? So let's plug in 1 minus 1/10. So this will be equal to summation n equals 1 to infinity of negative 1 to the n minus 1 times negative 1/10 to the n times 1 over n. And I'm allowed to plug in 1/10 because 1/10 is between negative 1 and plus 1. All right, so summation n equals 1 to infinity of negative 1 to the n times negative 1 to the negative 1. Then I have another negative 1 to the n over 10 to the n times an extra n. And so it's starting to get close to what I want. So this over here, I've got natural log of 9/10 is equal to this. So the natural log of 9/10 is equal to the summation n equals 1 to infinity of negative 1 to the 2n. Negative 1 to the negative first is negative 1. And then 1 over n times 10 to the n. Okay, now a quick side calculation is that negative 1 to the 2n, that's negative 1 squared to the n, which is 1 to the n, which is 1. And so this right here is simply equal to 1. So natural log of 9/10 is equal to negative summation n equals 1 to infinity of 1 over n times 10 to the n, which is the series I had in the first place. The only thing that's wrong here is I've got a minus sign. And so summation of n equals 1 to infinity of 1 over n times 10 to the n is equal to negative natural log of 9/10. Okay, and by one of the laws of exponents, I can rewrite this as natural log of 9/10 to the negative 1 or natural log of 10/9. And so the summation n equals 1 to infinity, 1 over n times 10 to the n, that converges to the natural log of 10/9. And I encourage you to try this on your calculator. If you plug in values of 1 here, so this is equal to, if I were to expand this out, this would be equal to 1 over 10 plus 1 over 200 plus 1 over 3,000 plus 1 over 40,000 and so on. Now, if you add these up, add the first few terms up, and then plug this into your calculator, they should be about the same thing. All right, and finally, number 6. Summation n equals 0 to infinity, 1 over 10 to the n. This right here is our familiar geometric series. That 1 over 1 minus x is equal to summation n equals 0 to infinity of x to the n. And this converges as long as x is between 1 and negative 1. And so if I replace n by a tenth, this will be equal to 1 over 1 minus a tenth. And so summation n equals 0 to infinity of 1 over 10 to the n. That is equal to 1 over 9 tenths. Or, of course, that's equal to 10 ninths. Summation n equals 0 to infinity, 1 over 10 to the n. And this kind of makes sense, right? Because if we were to start plugging in values here, we'd have 1 plus a tenth plus a hundredth plus a thousandth plus a 10,000th. And that's equal to 1.111111. There's a tenth, there's a hundredth, there's a thousand, there's a 10,000th, and so on. And I recognize that's 1 plus a ninth, which is indeed 10 ninths. Okay, so that's the exact values for these 6 infinite series.